B.
Buenos días. Good morning, sorry. Good morning. Welcome for another seminar in the Instituto Astrofísica de Andalucía. Today we will have the talk by Guillermo Muñoz Caro. He will speak about the experimental ice simulations for the interpretation of ice and organic conditions in the solar system. So Guillermo Muñoz Caro is coordinator of the interstellar and circumstellar medium research line at the Center of Astrobiology at the INTA-CSIC in Madrid. He's advisor of scientific proposals submitted to France, to United Kingdom, Germany, United States, and Poland. His research is dedicated to ice and dust processes in space leading to the formation of organic species and the organic fraction in interplanetary dust, comets, and meteorites, which could have triggered prebiotic chemistry on Earth. He gained international recognition with the first synthesis of amino acid under simulated interstellar conditions. He's also responsible of the ISAC ultra-high vacuum system at the Centro de Astrobiology Center in Madrid for the study of ice processes in space. He also participated in the instrument COSAC at Rosetta mission, and later led to the first in-situ detection of organic molecules on a cometary surface. So Guillermo, thank you very much for being here, for the acceptance of this talk, and the floor is yours.
Okay, thank you, René, and also thank you to Olga and Fernando for giving me the opportunity to give this presentation and hosting me here. The title of my talk is the experimental ice simulations for the interpretation of ice and organic observations in the solar system. And the presentation is divided in
Yeah, now it's working.
Now it's okay. All right. So the talk is divided into these sections. So first I will give an introduction that may also be useful for PhD students about the astrophysical and the lab context of dust and ice. Then I will talk about our experimental simulations of ice processes, the chemical and the physical side view, and finally, what we do to support observations and space missions. So first, I always start my presentations with this figure, where you can see the transit of matter in space. So from diffuse interstellar clouds, the dust enters dense clouds. It also goes the other way around. And in these dense clouds, you have formation of young stars with eventually with planetary systems. This material is processed through the cycle, and a fraction of it goes back to the interstellar medium. So this interstellar matter is processed. And finally, there is a connection with astrobiology, because this material from space, by impacts of comets and asteroids, seeds planets like our own, and as we will see, they may contribute to prebiotic chemistry. So this happens, we think, on Earth, and it also may happen in exoplanets. So, well, there are more than 100 species detected in the interstellar medium, but most of them are detected by radio telescopes in the gas phase, okay? While what we do is to study only 1% of the matter, which is the one contained in dust. And I like to cite this sentence from a reviewer of our recent paper that will be published soon. He said that it is amazing how grain and ice chemistry wants this mist as the last refuge of a scoundrel, which means el último escondite de un sinvergüenza, and considered only when gas phase efforts had failed, is now recognized as crucial in astrophysics, right? So 20 years ago, 30 years ago, like Fernando and Olga know well, the dust was something like, rather than something useful in astronomy. And now it is the other way around. This is also something that Fernando and Olga do here and in their lab. They study these processes in physical processes induced by dust, where you have scattering of the short wavelengths and you have absorption of the long wavelengths. So the scattering, the dispersion you see in the Pleiades very well. You see the effect of dust. So that's why the light is kind of bluish there. And the absorption of dust you see in dark clouds like this one. And also the reddening of the light. And the main tool we use to study dust is infrared spectroscopy, where you, thanks to these vibrations of molecules in the gas phase, but also in ice, in dust, we can measure the absorptions if there is an infrared source embedded in the cloud or outside the cloud as a field star. This light, which would be like a continuum of emission, if absorbed by cold dust, leads to these absorption bands. And this is what we measure. So now with the James Webb telescope, these are the typical spectra that are coming out of molecules in the ice covering the dust, and also the silicate particles, the absorption by the dust itself, right? So at the end, you have a composition of the ice, which is dominated by water and other molecules that I will be talking about. And even some COMS, complex organic molecules, are now being identified in the ice for the first time. So you end up with a model of a dust grain like this. This study of ices in space is relevant for interstellar ices, circumstellar, and also some pristine bodies in the solar system, like comets. So I will talk a little bit about the experiments we do in the lab with ices. You have multiple processes in the ice that can go on, starting with the accretion of molecules from the gas phase onto the cold dust to form the ice mantle, and then a process driven by energetic radiation. So these are photons, UV, X-rays, or comets, which are ionized particles. And at the end, you may end up, like we observed in the lab, with these COMS, these complex organic molecules made by the ice processing. So this is the lab we have at CAP. It's an ultra-high vacuum chamber to simulate the conditions in dense cloud interiors. And there are different tools. We have a hydrogen lamp to emit similar to the UV in the dense clouds. And so we prepare the ice mixture here, and we can do a spectroscopy in the UV, in the infrared, and we can also measure the molecules in the gas phase by mass spectrometry. Here you can see the window where we grow the ice. And this is an infrared transparent to do spectroscopy. And there you see the spot of the UV lamp that is more or less of the size of the window where we grow the ice. So we can irradiate it with UV. Here you see the expected secondary UV photons in dense clouds, and the fit with our hydrogen lamp. So the experiment basically consists on the ice growth and the irradiation. With mass spectrometry, we monitor the gas phase. With infrared, we monitor the irradiation, and also during the warm-up, we measure the masses of the molecules that are being ejected to the gas. Eventually, if you irradiate long enough, you end up with what we call a residue, which you can take out of the vacuum and analyze in a chemical laboratory. So I will talk a bit about the chemistry of this ice induced by radiation. I will show one of the simple examples. Would be you start with sulfuric acid, H2S. You grow your ice made simply of H2S. You irradiate it. You form radicals. These radicals recombine to make other molecules, and you can proceed adding radicals to make larger sulfur molecules, right? And you can also have the back reactions to reform H2S. And you can monitor in the infrared the formation of like H2S2, for instance, in these experiments, and also the larger species H2SX with X larger than 2. And if you warm up the irradiated ice, you see the ejection to the gas of molecules like H2S2, H2S3, H2S5, and so on at the different temperatures. So this would be like a simulation of a comet approaching the sun. So you see an increase of the temperature, and you see the ejection of the different molecules within the cometary ice. And we can also make mass spectra of the molecules, because we detect the fragments corresponding to a given desorption temperature, and we obtain the mass spectra of the different molecules. I will talk about this later regarding the MANIAC instrument that you are working on here. And you can also do Monte Carlo simulations to reproduce the experiments. So you start with this H2S ice here. So everything looks yellow. And as you form species, you see the different colors that are coming up first during the irradiation and later during the warm-up. And you can even, with these Monte Carlo simulations, this is the work of Stéphanie Cassot, you can reproduce the lab data. And this is very difficult from the theoretical point of view, but it worked nicely for these sulfur experiments. In the lab, when you extract this residue at room temperature, you can find very complex molecules. Regarding sulfur chemistry, you see all this. Sulfur 8 is the of sulfur on Earth. When you buy sulfur, this is mainly what you buy, sulfur 8. And it is formed very efficiently in these ice irradiation experiments. And we are interested in sulfur mainly because there is a sulfur depletion in the dense clouds and circumstellar regions. So one explanation is that this sulfur is hidden on the grains in the form of these sulfur chains, right? That is the interest from the astrophysical side on sulfur. If you do this for other molecules that are known to be in the ice, you have these intermediate species which are very reactive to form more complex species, and eventually in the residue you find all these families of molecules. So from the chemical point of view, this is very complex, what is going on if you introduce irradiation in the ice made of these molecules, so water, methanol, CO, CO2, ammonia. And for instance, if you consider ice, warm ice, you tend to polymerization of the species. If you introduce water, which is physical, you end up with many different molecules in these residues. this is a picture of one of these residues containing all those species. Yeah. So basically, what you do is you irradiate the simple molecules, you form radicals. The radicals recombine to make larger molecules, and these are the ones that at room temperature after the sublimation of the ice. So this is a typical composition of these residues. You see that, for instance, this nitrogen heterocycle is very abundant, and it is a precursor of this other heterocycle known as HMT, hexamethylene tetramine, which is very abundant on residues, and it was detected in some meteorites by a Japanese group. It was also searched for in comets, but not found yet. And you can also do infrared spectroscopy of the residues, and you see that this band, known as the 3.4 micron feature in the infrared, is characteristic of molecules with OH groups attached to CH2 groups. And in fact, sometime later, they discovered a lot of supers in these residues. So these are the molecules with the OH groups next to the CH2 groups. And one of them is ribose here, which is of prebiotic interest. Our most famous work is the synthesis of amino acids by radiation of ices. I don't want to extend a lot on this because I want to talk also about the physics of the ices. Some of these amino acids were with two amino groups, two NH2 groups, were found in the Murchison meteorite. So because we were criticized because of the fact that there were no these diamino acids in meteorite, so we searched for them in Murchison, and they were also there. So it supports that a similar chemistry is going on in space. And these diamino acids are precursor of what is known as the PNA, which is a precursor of DNA. So it's a more stable version of DNA, which can remain outside living beings. Very lately, we are interested in the synthesis of nucleobases like adenine. So we thought that imidazole would be a precursor of some of these nucleobases. And last week, my student, Carlos, detected imidazole in the residues. So this is something that I did during my PhD time. We stopped working on this prebiotic chemistry, and now we are getting back to it. And one of the things we observe is that independently of the type of radiation, whether you use UV or X-rays or even ions simulating very energetic cosmic rays, we end up with similar products. So a possible explanation is that the starting blocks to make complex molecules, these are fragments, radicals, reactive species like formaldehyde. They are not so many. If you start with water, methanol, ammonia, typically, or adding CO instead of methanol. And so because of this, it doesn't matter so much the kind of radiation that you use to irradiate the ice. You end up with similar compounds. Okay. So here I just want to show an example of X-ray processing that we do in Taiwan at the synchrotron there. And in this case, we used an ice composition with water, ammonia, and methane at the bottom of the ice. And on top, we put CO and methanol to make it astrophysically relevant. So we irradiated with the X-rays, and this we formed and that were ejected during the radiation to the gas were these. There is no methanol there, even though there was methanol in the original ice. And the funny thing is that this composition matches very well the one observed with ALMA on the protoplanetary disks. So it is, I show this because it is very difficult to compare what is observed with what we do in the lab, but in this experiment, it seemed to work quite well. Okay, so let me talk a bit about the physics of these ice processes. First of all, we monitor and we keep the data during the experiments regarding the temperature, pressure, what we measure with by mass spectrometry, and we also have a laser to measure the variations in ice thickness, and of course the infrared to monitor the ice column density. So we can, with this set of data, we can, for instance, use the column density of the ice and the ice thickness to get the infrared band strengths. This allows astronomers to estimate column densities, like with the James Webb. We also measure the volumetric density of the ices and the optical constants, N and K, which are very important also for astronomy, because with these optical constants, so N is the refractive index, K the absorption, you can produce spectra, and you can use different morphologies of the ice, so a spherical grain or a more elongated one, so that you can reproduce more realistic spectra, so to say, okay? And even maybe convert these absorbance infrared spectra to reflectance, which is very useful for the ices in the solar system. We are working on this topic now. So we are doing these measurements for different ices. Here is an example of the optical constants for CO, pure CO ice. We have done it for a few ices now, okay? So that is, the estimation of the density of the ice using the column density in the infrared and the ice thickness from the laser. We also measure the UV absorption of different ices, which you can see here. This is important because you know how much of the UV is absorbed by the ice and the dependence with wavelength. So we get the absorption cross sections in the UV of the ice, which were not, most of them were not measured before. And we have spent also years studying photodisruption, which is basically the absorption of UV in the ice and the eventual ejection of molecules as the result of this UV absorption. It is important for astronomy because, like in dense clouds, you see molecules in the gas phase, and with the time scales of 1 million years and the cold temperatures, they shouldn't be there. They should all be sticking onto dust. So there must be a desorption process that is not driven by temperature, and this could be photodisruption. Okay, so this photodisruption, we know it is dependent on the temperature that you use to grow the ice, whether you grow it at 10K or at 50K. You see that the degree of disorder in the ice, so this would be like a crystalline CO ice, and this would be disordered or amorphous CO ice. This degree of disorder affects the efficiency of the photodisruption. About the density of the ice, you can estimate the density at different growth temperatures. So in the case of CO, you see this tendency, you have like a plateau between 15 and 20K. You have an increase, which is due to crystallization. So when the ice crystallizes, the density increases. And you see the opposite. If you grow the ice at the lowest temperatures, you see that the degree of disorder is also influencing the density of the ice. We have done this work in collaboration with the Alcoy group, with Satorres group. And we have also done something new, which is colorimetry of the ice. In the case of CO, we observed that if you grow the ice at 8K and you warm it up, the color doesn't change. But if you grow it at 8K or in a different experiment, you grow it at 11, 13, you see that the ice changes color. So at this temperature, this is a light at the back. This white color is not related to the ice. This is the light at the back. So this is the real color, meaning that it becomes transparent because it crystallizes. So I like a lot this result because you see by eye, just looking into the chamber, the crystallization process of the ice and at which temperature is occurring. And also you see that pure CO ice is brown. So if you think that brown is related to organics in some moon, be careful because it could simply be some pure ice. And it also tells you that diffusion is not important when you warm up the ice. So the molecules don't get, in the case of CO ice at least, they don't get enough mobility to rearrange, making an ordered ice. But if you grow it at different temperatures, then if you grow it at the high temperatures, directly you are making crystalline ice. Okay. We compare here the color temperature of the ice with the photodissorption yield, and you see that if you warm it up, it doesn't change much in both cases, but if you grow it at the different temperatures, it follows a similar behavior. So it means that photodissorption is sensitive to this ordering of the ice. And to go back to this photodissorption process, we observe two tendencies in the different irradiation intervals. So here you turn on the lamp, here you turn it off. You see sometimes a rather constant, this is not the best data now, a rather constant signal, and other times you see an increasing signal. So I will not discuss this because it takes more time, but I will discuss the constant photodissorption, which we call photochemical desorption or photochemic desorption. And this is basically basically this is we think the reaction of radicals on the ice surface making a product like methane when you irradiate methanol ice, and this with the excess energy of the formation, this methane on the surface will immediately desorb. This is what we call photochemical desorption. And you can also observe photochemical desorption of some comets like ethane and propane in the methane irradiation experiment. So this is a way to eject large molecules from the ice so that they can be detected with radio telescopes. And finally, I will talk about the application to observations and space missions of our work. So for the JWST mission, Jupiter Icy Moons mission, we did some experiments using the climatic chambers at INTA to reproduce cold temperatures and warm up the ice. And we used a bucket. So we are not talking anymore about microscopic ice. This is a regular box where we grow the ice and we monitor the temperature. We measure the thermal conductivity of the ice. And furthermore, this ice is a solution with salts, like you have in Europa and other ice. So we measured the desorption of the molecules as you warm up the ice. And the thermal conductivity also behaves kind of linearly with temperature. And we also observe these spikes, which are changes in, it's an artifact of the way we measure thermal conductivity. But the interesting thing is that this artifact is due to heat that is being liberated by the ice during a structural change. So if the ice crystallizes, heat is released within the ice, and you see this spike in the thermal conductivity. So it's a very sensitive way to spot structural changes in these ices with salts. We have also, we are working with James Webb data. So in particular, and this is something for Olga and Fernando, we are also interested in porosity. So we came in contact with physicists at ITEFI CSIC, to use ultrasound to measure porosity, which is totally crazy. But we got an Explorer project to do this, and we could just play with it. And we started using this transducer, which is emitting an ultrasonic pulse. We just put a water drop on it, and we freeze the drop. So we measure the transmittance of ultrasound through liquid water and also through water ice. And well, we measure different velocities of propagation of the signal. And we used a model from this group so that we can, for instance, for a given experiment, we can see what is the porosity level. So this is 10% corresponding to each ice. So it's, you know, something we wanted to try. We haven't done it in the vacuum chamber, but well, in principle, you can do it. The challenge is you are working with ultrasound in vacuum, but it works. If you get enough money to do it, you can do it. And this is quite breaking results. We also simulated the drop. We introduced some porosity on the drop, and you can see the transmission of the pulse and also the reflections. Like here, you see it. The ultrasound reaches the surface of the drop, and then it goes back. When there is little porosity, you see a much better reflection. When you increase the porosity, you lose a lot of ultrasonic signal. But the important thing is that you can relate this to a porosity level. So we used with Stephanie Cassot recent James Webb data in Europa and Ganymedes. And we have published that paper. One of the things we have learned is that you can, with the infrared observations, you can say something about porosity ice. So in particular, in the DFT simulations, you can make a pore in CO2 ice, and you see the effect of the pore in microscopy. So this band here is not there if there is no porosity in the CO2 ice. So because this band here is observed, we think that there is porosity in the CO2 ice in Europa and Ganymedes. We have also participated in cometary missions. Before that, I worked with interplanetary dust. That I asked NASA to get some of these dust particles collected in the stratosphere at 20-kilometer altitude. And I was interested in the organic fraction of them. So we characterized the organic composition of IDPs with this type of amorphous carbon. And I also got NASA Stardust particles when I was already in Spain. I got 6 of these particles, and we did infrared spectroscopy on them. these are the spectra. They are characteristic of amorphous carbon, but we doubted whether it was indigenous from the comet or some contamination in the aerogel. I have worked as a co-I of the COSAC instrument in the ESA Rosetta mission. So COSAC is a gas chromatograph with a mass spectrometer that you can see here, the instrument. And so you warm up the sample, the cometary sample. It goes through a column, and at the end you can do mass spectrometry of the sample. So we were very excited during the landing on the comet 67P when we got all these packages of data coming down. But unfortunately, they were empty or almost empty because of the bad landing of Philae on the comet. So that was very unfortunate because our instrument was working very well, but it seems that there was no sample there. So that was very unlucky. But the lucky part was during the first landing. There were 3 landings. So during the first landing, if you look here, you see that a small cloud there, and this was some ejected dust from the comet during the landing. And this dust entered the exhaust tube of our instrument just by chance. Of course, it was not planned, right? But because of that, we could measure with a mass spectrometer. This was before the dust was ejected, and this is after. So you see an increase of the masses, right? And I worked on the characterization of the molecules that were in this cometary dust. And you see that they are COMs. They are relatively large molecules. So we were happy with this result. And furthermore, you can see that most of these molecules in the comet can be made by 2 radical reactions, like it happens in the ice experiments. It was also not very fortunate, the measurements with infrared on the surface of the comet, because the spectrum was quite shallow, as you can see here. So it was compared to our residues, but it is not conclusive because of these shallow features on the comet. Very recently, a few months ago, they also did infrared spectroscopy of Hayabusa 2 samples from asteroid Ryugu, and they compared it to our residues. So you can see here, the 4 in black are our residue spectra, and these are Hayabusa spectra. So you can see very clear similarities between both. So the conclusion is that, at least spectroscopically, the Hayabusa samples, they are compatible with the residues we make by ice irradiation. And I am getting to the end of my talk. I hope I didn't talk too long. For future projects, I would like to continue working on asteroids, at least collaborate with these groups. And regarding comets, until recently, we have still been publishing some works on Rosetta. And if you're interested, I would also like to collaborate in the middle term future, I don't know, with you on the MANIAC instrument of Comet Interceptor. In particular, we can provide the desorption temperature of the molecules in the comet, and also the mass spectra that we are obtaining in the lab, so that we can, with the MANIAC data, in principle, we can provide this database of mass spectra to characterize what is being measured by MANIAC. So we can do it for like sulfur molecules or for any, well, not any other molecules, but for other molecules, so to say. So we have to synthesize these molecules in our ice irradiation experiments, and then obtain the mass spectra for comparison with MANIAC. So if you're interested, you just let me know, and we can do something together. So I would like to thank my group of my closest group, people working with me in the lab: Bruno, Rafael, Carlos is the PhD student, Hector, and Cristobal, and also the external collaborators. Okay, thank you.
Thank you very much, Guillermo. So now, questions for Guillermo for the talk?
Was it too long?
No? Perfect.
Ah.
Any question?
Yeah, we have discussed that before, but I guess including some dust in your ultra vacuum chamber is not a good idea.
We can, if we can put it on a surface, the cold surface where we grow the ice, or not grow the ice, but put the dust analog on this cold surface to do spectra and in situ spectra in the UV, in the infrared, and also irradiate it to see what happens. We can do that either at cold temperature or just using the spectrometers. Yeah, or like I think I tried years ago when we were in this network, used dust powder and deposit it on a plastic that statically traps the dust to do a spectroscopy of these dust particles. Yeah, like now it is with the James Webb. They have found that the size of the dust has an influence on the infrared spectra that they are measuring. So they have concluded that the average dust grain size is a little less than 1 micrometer in diameter.
The spectra is the level of the spectra or something?
It is some features like scattering is, as you know, related to the dust size, and the scattering is observed by like the formation on the infrared absorption bands that they measure. So from using modeling of dust size distribution, they come up with this almost 1 micron diameter of the, on average, of the dust grains. Yeah.
Questions in the room?
Guillermo, I have seen you have presented some work on the CO2 ice of Ganymedes. I'm just on one of the James Webb data consortium, but I think it's what's the name of the girl there in France? Bokele.
Bokele.
Looking at that. Are you in contact with them or?
Not with Bokele. I share Erasmus students with Delft University, and my collaborator is Stéphanie Cassot, also French, but she's in Delft, and so we get students from Delft to our group to work with us in the lab, and the collaboration is mainly based on this student. So it was a student that did the experiments with water and CO2 ice. And then these lab experiments were used to fit the James Webb data on these moons. And then there is another guy, Bruno Escribano, who is doing the DFT synthetic spectra to understand, to interpret the different absorptions in the spectrum. So with this combination of observations, lab, and calculations, you can get an in-depth knowledge of the ice. And this is, I think, what we should be doing now, because with the new James Webb data at the end, what you see is that the molecules you observe are the same that were observed 20 years ago or 30 years ago even, right, with a smaller telescope. So what we should be doing is to understand more in depth not only the ice composition, but whether the molecules in the ice are mixed or if they are layered, if there is porosity in the ice or not. We should go to this level of detail now, because the James Webb data is at very high resolution and allows a proper comparison with the lab data.
Yeah, that's really very interesting, because I found that some asymmetry in the hemisphere of the Ganymedes between the
Yes.
north and the south, and I wonder
Yes.
whether this kind of mechanism could explain things
Yeah.
that they don't really know.
Well, in the paper we give some explanation about these asymmetries, because you have some parts that are more processed than others by radiation. So and you see that in the spectra of the ice. You see that the ice spectra are not the same in the living hemisphere and the other one. So we provide some explanation for that
On the physical process.
on the physical processes, because this is not like the interstellar ices that I am more used to. This is relatively nearby, and you see the effect of diurnal cycles on the ice. So it is very, very interesting and also very demanding, because you need to explain what is happening during the day and during the night on these moons, right? So yeah, this is now cooking at the moment. Yeah.
I have another issue, very curious or technical question about how do you measure the temperature of the ice when you have such small sample in a chamber?
Yeah. We have silicon diode sensors that are on the surface where we grow the ice. So yeah, this is basically how we measure it, and then we compare, like when you warm up the ice. In the case of water, you see the desorption is happening at a certain temperature, typically 170 K in the lab. So you see whether this temperature matches the one measured by other people in the lab, right? And we all tend to get the same temperature value. So that gives you also on what you are doing.
Measuring a given thickness, and you are really sensing. Are you sure you're sending not the top of that or in the middle?
It's more at the bottom. So we are not measuring directly the temperature of the ice, but the closest as possible to the ice. Like, yeah, this is typically what we all do. And now we are working on a paper where we extrapolate this temperature measured in the lab to the astrophysical temperature. Because if you talk to an astronomer, he will tell you that water ice is not formed at 170 K, but at 110 K. And you arrive to this value if you extrapolate the vacuum level in the lab to the real vacuum in the interstellar medium, which is like still 2 orders of magnitude better vacuum. So about 2 orders, yeah, compared to the ultra high vacuum. It's still like 2 orders in a dense cloud. In the diffuse medium, so 10 to the 6 particles per cubic centimeter is more or less as good as we can do in the lab, right? In any ultra high vacuum system. So if you do this extrapolation to the real pressure, you arrive to this 105 K for water growth. Yeah.
Thank you.
Any question on the room? We can go for the Zoom. There is a question on Zoom. Javier, please.
Hi, a very nice talk, Guillermo.
Thank you.
Enjoy it very much. We are working with James Webb observing trans-Neptunians and centaurs. Soon will appear 2 papers we have with the Noemi Pinilla program, the DISCO TNOs program with tens of spectra of trans-Neptunians and a few centaurs. And one of the things that we notice is that there is a class of TNOs that basically the spectrum is water ice, some CO2, other minor species, dust, and nothing else. But the interesting thing here is what I'm pointing in the question is that when you have centaurs, the centaurs are scattered TNOs that go inside and warm. And as part of this warming process, they start to sublimate water in some way, and not necessarily because because of the solar irradiation, but they start to be covered by amorphous dust and ice, and as soon as you go to the more evolved ones, you start to see only the 3 micron band, shallower and shallower as soon as longer is the period they warm and are active. So I am interested in if there are laboratory experiments on intimate mixture of amorphous dust, like the cometary dust, right, and water ice, that can be used to compare to what it is observed, because as soon as the object is almost fully covered by dust, and with some, but my hypothesis is that there is some water ice still mixed with this. You have a very shallow 3 micron band, similar to what we observe in Churyumov-Gerasimenko, for example.
Okay.
And but some author claims that this is not water ice; it is something else. And well, I'm not sure if there are if there are experiments in the lab. I know very well, for example, that in primitive meteorites, carbonaceous chondrites, you have hydrated minerals plus water in the spectrum.
Yeah.
But hydrated minerals produce very deep bands at 2.7 and 2.8 are very easy to detect, but not that of amorphous dust.
Yeah.
So
Yeah.
back to the question. You know if there are experiments or
Yes, there is a group in Jena, in Germany, of Cornelia Jäger and Harald Kruger. They have mixed dust in the ice, and they have studied the effect of the dust on ices. So I can send you this contact if you're interested.
Oh, if you have any reference, I can read.
I can send you the reference. Yeah.
So, but you don't have this kind of experiment planned in the.
We haven't done them ourselves to mix the dust with the ice. We haven't worked on that. We could do it in principle, but we haven't done it. One of the reasons why we didn't do it is because if you are working with best vacuum conditions and you put dust in there, you pollute the chamber. So for this, you need a Porter vacuum so that you can clean the chamber more easily. But it can be done. Yeah. And these people, the last few years, they have been working on these experiments, mixing dust with ice and see what is the desorption temperature of the molecules in these experiments and the effect of the dust. Yeah.
Thank you very much.
Thanks to you.
Thank you. Questions in the room? Okay, thank you. So
Thank you all for coming. Yeah.